Hi, welcome to Sunil Maths tutorial, functional analysis, class number 15. In this video, we prove a theorem. Let us see the statement. If capital M is a closed linear subspace of a normed linear space capital N and x0 is not a vector, x0 is a vector not in capital M, x0 is a vector that is does not lies in capital M, then there exists a functional f naught in n star such that it satisfies two properties. F naught of m is equals to 0 and f naught of x naught not equals to 0. So right, first we write the introduction part of this theorem. They given that capital N is a normed linear space. Capital N is a normed linear space and capital M is a closed subspace. Capital M is a closed subspace of capital N and x naught is a vector, x naught is a vector not in capital M, not in capital M, that is x naught does not belongs to M, x naught does not belongs to M. So right, define or consider a functional, in another words, consider a natural mapping, consider a natural mapping. Natural mapping means it is defined from space into quotient space. Consider a natural mapping. Capital T maps n into n by m such that it is defined like this. T of x is equals to x plus m for all x belongs to capital N with the property norm t less than or equals to 1. So right, we define a mapping capital T that maps from capital N into the quotient space n by m, satisfying the condition T of x is equals to x plus m for all x belongs to capital N with the property norm T of x is equals less than or equals to 1. So right, since capital M is closed subspace, since capital M is closed subspace of capital N, then obviously n by m is a normed linear space, is a normed linear space with the norm of a coset, with the norm of a coset, norm with the norm of a coset. Coset means x plus capital M, which belongs to n by m, and the norm is defined by norm x plus m is equals to infimum of norm x plus small m such that small m belongs to capital M. Small m belongs to capital M. We observe that this is true every time whenever M is a closed linear subspace. M is a closed linear subspace of a normed linear space capital N. Then obviously the quotient space is also a normed linear space with the norm of the coset x plus m that is defined like this, infimum of norm x plus m such that m belongs to capital M. Now we show that capital T is a continuous linear transformation. Now we can prove that capital T is a continuous linear transformation. Continuous linear transformation. So right, first one, to show that T is linear. To show that capital T is linear. So to prove that capital T is linear, let us consider two elements. Let us take two elements, x comma y belongs to capital N and two scalars alpha comma beta belongs to capital R, are field. Now T of alpha x plus beta y is equals to, what is the definition of T? See here, T of x is equals to x plus m. T of x is equals to x plus m. By using the definition, T of alpha x plus beta y can be written as alpha x plus beta y plus capital M. Now apply the definition of addition of cosets. Addition of cosets. Alpha x plus m plus beta y plus m. Again, addition of scalar multiplication of cosets. It can be written as alpha into x plus m plus beta into y plus m. Again, by applying the definition of t, it can be written as alpha into t of x plus beta into t of y. Therefore, we prove that t of alpha x plus beta y is equals to alpha into t of x plus beta into t of y for all x comma y belongs to capital N and alpha comma beta belongs to the real numbers capital R. This condition shows us t of alpha x plus beta y is equals to alpha into t of x plus beta into t of y shows us capital T is a linear transformation. Therefore, capital T is a linear transformation. Next, in the second case, you have to show that capital T is continuous. To show that capital T is continuous. Capital T is continuous. Right. To prove that capital T is continuous, we use the definition of norm. By definition of the norm we have norm T is equals to, or norm T of x. Norm T of x is equals to norm x plus m, which is equals to infimum of norm x plus m such that small m belongs to capital M, which is less than or equals to norm x plus small m for all m belongs to capital M. In particular, what happens if small m is equals to 0? If small m is equals to 0, then norm T of x is less than or equals to norm x. Norm T of x is less than or equals to norm x. This condition shows us capital T is bounded. Capital T is bounded. Further, additionally, T is bounded means obviously T is continuous. We move one more step. Norm T is equals to supremum of norm T of x such that norm x less than or equals to 1, which is less than or equals to supremum of norm x, because norm T of x less than or equals to norm x such that norm x less than or equals to 1. This is again less than or equals to 1. So you show that norm T is less than or equals to 1. It means T is bounded. T is bounded. Whenever T is bounded, then T is continuous. It means from these two cases, we conclude that therefore capital T is a continuous linear transformation. Capital T is a continuous linear transformation. So further, let us apply here. For any small m belongs to capital M, T of small m is equals to small m plus capital M by definition. So this is nothing but m, because of small m plus capital M is zero element in capital N by M. So because small m belongs to capital M, obviously this m plus m is equals to capital M. So T of m is equals to capital M. And it is the zero element. In capital M. for all small m. This condition holds for all small m, that is T of m is equals to capital M for all small m belongs to capital M, and that is the zero element in n by m. Therefore, we conclude that T of capital M is equals to 0. T of capital M is equals to 0. Now since already we said that x naught is a non-zero element and that does not belongs to capital M. So T of x naught is equals to x naught plus capital M, which is clearly not equals to 0. Which is clearly not equals to 0 because x naught is a non-zero element. So right, now we use the previous theorem to prove the extension by previous theorem. This theorem is explained in video number 13. I think video number 14. Video number 14. This theorem explained in the previous theorem, just previous video of our lecture. So what is the statement of that theorem? If capital N is a normed linear space, and x naught belongs to capital N, then there exists a functional f naught in n star such that f naught of x naught is equals to norm x naught and norm f naught is equals to 1. Clearly, this is previous theorem. Applying this theorem to our theorem in this video, we get there exists a functional f in n by m star such that satisfying the condition f of x naught plus m is equals to norm x naught plus m and norm f is equals to 1. So we are applying this theorem. If n is a normed linear space and x naught belongs to n, then there exists a functional f naught in n star such that f naught of x naught is equals to norm x naught and norm f naught is equals to 1. This theorem explained in 14th video. So applying this theorem to present theorem, there exists a functional in n by m star such that f of x naught plus m is equals to norm x naught plus m and norm f is equals to 1. So now we define one more functional. Or we define a mapping. We define f naught as f naught of x is equals to f of t of x. F naught of x is equals to f of t of x for all x belongs to capital N. First we show that this f naught is linear. We prove that this f naught is linear. To prove that f naught is linear, let us consider f naught of alpha x plus beta y. By definition of f naught of x here, f of t of x. So f of t of alpha x plus beta y. Here in this theorem, already we prove that capital T is a linear transformation. And it satisfies the condition t of alpha x plus beta y is equals to alpha t of x plus beta t of y. Applying that condition here, it can be written as f of alpha t of x plus beta t of y. Again, f is also a functional. So f is also a functional. It can be written as alpha f of t of x plus beta f of t of y. Right. Again, f of t of x can be written as here. F of t of x can be written as f naught of x. So it can be written as alpha f naught of x plus beta f naught of y. Finally, we prove that f naught of alpha x plus beta y is equals to alpha f naught of x plus beta f naught of y. This shows us f naught is linear. This shows us f naught is linear. Now we have to show that f naught is bounded. To prove f naught is bounded. To prove f naught is bounded. So write norm f naught of x. Norm f naught of x is equals to norm f of t of x. F of t of x, which is equals to norm f norm t of x, norm t of x, which is less than or equals to norm f into norm x, because norm t, we proved that norm t is less than or equals to 1. So this condition shows us norm f naught of x is less than or equals to norm f into norm x. And we know that this f is already bounded function. This f is already bounded function. F is bounded. F is bounded. This shows us f naught is also bounded. F naught is also bounded. If f naught is bounded, we know that every bounded linear transformation is continuous. F naught is continuous. F naught is continuous. Hence, f naught is a functional. F naught is a functional on n star. F naught is a functional on n star. So right, further, this f naught is an extension of f and it is a functional on n star. Further, you have to show that one more condition. If small m belongs to capital M, if small m belongs to capital M, if small m belongs to capital M, then f naught of m is equals to f naught of m is equals to f of t of m, which is equals to f of 0, which is equals to 0. Already we proved that t of m is equals to m for all 0. Hence, this condition applies as f naught of capital M is also equivalent to 0 for all small m belongs to capital M. For all small m, for all, not small m, for all subspaces, closed subspaces, capital M is subset to capital N. F naught of M is equals to 0. So right, and we go for further, f naught of x naught is equals to f of t of x naught, f of t of x naught, and t of x naught is defined by, already we defined t of x naught is equals to x naught plus capital M. We know that x naught not equals to 0. Obviously, x naught plus m is also not equals to 0. This condition implies as f of x naught plus m is also not equals to 0. It means f naught of x naught is also not equals to 0. Hence, you observe that f naught of capital M is equals to 0 and f naught of x naught is not equals to 0. So from these conditions we prove that we complete the proof of our theorem. Hence there exists a functional, in n star satisfying the above properties. F naught of m is equals to 0 and f naught of x naught is equals to 0. This completes the proof of our theorem. So remember that n star is nothing but the set of all continuous, linear transformations, the set of all continuous linear transformations from capital N into either real linear space, either real or complex numbers field. Remember that n star is the set of all continuous linear transformations of n into either R or capital C. In the next video, we prove one more theorem in a similar manner, satisfying some different conditions. F naught of m is equals to 0 and f naught of x naught is equals to m 1 unit 1, and norm f naught is equals to 1 by d. 1 by d. In the next theorem, in the next video, we prove this theorem. So keep learning. Wish you all the best.